Morning to everyone. From the definition, we can have H is a normal subgroup of G if and only if XH X inverse is contained in H. XH X inverse is equal to XH X inverse such that H belongs to H and X belongs to G. H is a normal subgroup of G if and only if XH H inverse is contained in H. The improper subgroup H is equal to singleton E is also a normal subgroup of G. E belongs to H implies X E X inverse belongs to H for all X belongs to G. The improper subgroup H is equal to G is a normal subgroup of G. If H is equal to singleton E and H is equal to G are called improper or trivial normal subgroups of G, and all other normal subgroups of G if exist are called proper normal subgroups of G. If N is a normal subgroup of G, then we can write we can read it as N is a normal subgroup of G. Any non-abelian group whose every subgroup is normal is called a Hamilton group. So theorem 1, a subgroup H of a group G is normal if and only if XH X inverse is equal to H, comma, for all X belongs to G. So first we have to prove that if a subgroup H of a group G is normal, to prove that XH X inverse is equal to H. And after that, conversely we have to suppose that H is a normal subgroup of G, and to prove that XH X inverse is equal to H. So let G be a group and H be a subgroup of a group G. To prove that H is a normal subgroup of G, that means XH X inverse contained in H. So first we have to suppose that XH X inverse is equal to capital H. So XH X inverse is always contained in H. That is from our result note 1. Therefore, H is a normal subgroup of G. Conversely, suppose that H is a normal subgroup of G. So now we have to show that XH X inverse is equal to H, and for all X belongs to G. Clearly, XH X inverse contained in H, and first let us assume that X belongs to G and implies X inverse belongs to G. Why? Because X is an element of a group G. So every element of a group G has its own inverse. So X belongs to G implies X inverse belongs to G. So therefore X inverse H into X inverse whole inverse is contained in H. So X inverse HX is contained in H. So X into X inverse HX into X inverse belongs to XH X inverse. Therefore H is contained in XH X inverse. Therefore from 1 and 2 XH X inverse is equal to H for all X belongs to G. Therefore H is a normal subgroup of G if and only if XH X inverse is equal to H for all X belongs to G. So this is the proof of H is a normal subgroup of G if and only if XH X inverse is equal to H. So coming to next theorem, prove that a subgroup H of a group G is a normal subgroup of G if and only if each left coset of H in G is a right coset of H in G. That is, H is normal subgroup of G if and only if XH is equal to HX. So here also first we have to prove that H is a normal subgroup of G. Then we have to prove that XH is equal to HX. That means each left coset of H in G is a right coset of H in G. So first we have to assume that H is a normal subgroup of G, and we have to prove that each left coset of H in G is again a right coset of H in G. So H is a normal subgroup of G. Implies XH X inverse contained in H. Implies XH X inverse is equal to H. So XH X inverse into X is equal to HX. Implies XH is equal to HX. So conversely, suppose that XH is equal to HX. So now we have to prove that H is a normal subgroup of G. So H is a normal subgroup of G means we have to just simply show that XH X inverse is contained in H. So XH is equal to HX. So every element of left coset of H in G is equal to right coset of H in G. So every element has its own inverse. So we have to pre-multiply the X inverse on both sides. XH into X inverse is equal to HX into X inverse. So XH X inverse is equal to H into X inverse is equal to E, since by inverse law. So XH X inverse is equal to H. So automatically from note 1, XH X inverse is contained in H. Therefore H is a normal subgroup of G if and only if XH is equal to HX. Therefore, hence the theorem is H is a normal subgroup of G if and only if XH is equal to HX and comma for all X belongs to G. And next theorem, a subgroup H of a group G is normal subgroup of G if and only if the product of two right cosets of H in G is again a right coset of H in G. So now the proof is, let G be a group and H be a subgroup of G. So suppose that H is a normal subgroup of G. So let A comma B belongs to G implies A dot B belongs to G, since by closure law G is a group means G satisfies the closure law. So HA comma HB comma HAB are right cosets of H in G. Now consider HA dot HB is equal to H into AH of B. So H of HA is into B. HH into AB is equal to HAB. The product of two right cosets of is also a right coset of H in G. So H is a normal subgroup of G. HA dot HB is equal to HAB. So conversely, suppose that product of two right cosets is again a right coset of H in G. HA dot HAB is equal to HAB. Now we have to show that H is normal subgroup of G. Let X belongs to G and H belongs to capital H. XH X inverse is equal to E into X. X into E is also is equal to E into X, since by identity law. So EX into HX inverse. So EX can be written as HX and HX inverse. So that belongs to capital H. XH X inverse belongs to capital H. Therefore H is a normal subgroup of G. HA dot HB is equal to HAB. Implies H is a normal subgroup of G. Therefore, hence H is a normal subgroup of G if and only if HA dot HB is equal to HAB. Next theorem, prove that every subgroup of an abelian group is normal subgroup. So here also we have to show that G is an abelian group and H is a subgroup of G. We have to show that H is a normal subgroup of G. So H belongs to capital H and X belongs to G. So H is equal to E dot H and E can be written as X into X inverse. Why? Because that is an inverse property. X into X inverse is equal to X inverse into X is equal to E. So X inverse into H. So X of X inverse into H is equal to X into H X inverse. So that is equal to XH X inverse. So XH X inverse belongs to H and H belongs to capital H and X belongs to G. Therefore, H is a normal subgroup of G. Hence, every subgroup of an abelian group is normal. So, these are the theorems for first subgroup of a group G. So, tomorrow we will discuss about another theorems. The intersection and union of a normal subgroups is again a normal subgroups of group G. So, any discussions, please contact me. Thank you.